All right, I think we can get started. So we're going to talk about Kubernetes. And hopefully you have seen a little bit more about Kubernetes than just the keynote just now, because it is going to be a bit of a deep dive. But even if not, then I think you should get plenty out of this talk anyway. So my name is Paul. I'm from the Netherlands. I work for a company called Luminous. And I wrote this book about OSGI. So you might wonder, why is an OSGI guy talking about Kubernetes now? So during the projects that I was involved in the past few years, I've been involved in quite a few projects where we had quite large cloud deployments. And based on that experience, I started leading a project in Luminous where we started evolving our infrastructure that our teams built on towards a Kubernetes-based infrastructure. So in the past half year or so, my work has been centered completely about Docker, Kubernetes, writing cool stuff in Golang, etc. So a bit different from what I've been doing before that. So the talk will be about the following. We're going to take Kubernetes. We're going to take Kubernetes as a basis. But once you start getting into Kubernetes, you will see, well, first of all, it's an extremely cool tool. I'm very happy that Kubernetes is out there. It's probably the best clustering software that is available right now. But when you start using it and start looking at all the getting started guides that are out there, well, they're getting started guides. And you see that they don't really get you to a production level environment. There's still a lot of stuff missing. So I will take you through 9 steps, kind of the steps that we went through actually building a production environment on top of Kubernetes, and show you the other necessary tools and steps you have to take to actually make this usable in such an environment. Because Kubernetes is just a tool. It does quite amazing things, but we need a bit more than just Kubernetes, as it turns out. So let's get started with it. And because I can imagine that, not everyone is working with Kubernetes on a daily basis yet, we start with a step 0. So this is not included in the 9 steps. And we will get our terminology and concepts straight around Kubernetes so that we actually have a good basis to start working on. So if you talk about Kubernetes, there's a few concepts that you should really understand, to be able to even use it, and especially to be able to build on top of it. So the first concept that we're going to see is the concept of, the fact that there is a master node in a Kubernetes cluster. And this master contains an API. So we can just use REST to talk to the Kubernetes master and, do stuff with Kubernetes. And one of the things you can do with this API is define replication controllers. And a replication controller kind of defines that you have some container that you want to run in your cluster, and it defines how many replicas of that container should be running. So for example, I have some container defined, and I tell Kubernetes that I want to have 10 replicas of that specific container. When I tell this to or when I define this replication controller on my master, Kubernetes will then take care of actually starting this container on 10 different nodes. And every running container that we have is called a pod. So this pod is actually an instance of my application, so to speak. And the replication controller will just take care of making sure that I have enough replicas. If one of the containers crashes, for example, the replica controller will notice that and it will start this same container on another machine. So we have the concept of nodes, which are kind of my physical machines. We have the concept of pods, which are instances of my running application. And we have the replication controller that keeps everything scheduled. So if you want to actually start using this and start deploying something in a Kubernetes cluster, what do? Well, looking at the getting started guides out there, it will look like the following. So first of all, of course, you have to have a Docker container. We're not going to go into how to do that. I assume you all know that. But you push your Docker container to some kind of repository. And then the next first step is you define a replication controller. And the basic way to do that is just create a JSON file, and this JSON file contains the definition of such a controller. We then use a command line tool called kubectl, and we pass in this configuration file, and by that we create this controller in my Kubernetes cluster. And the replication controller on its turn will actually start creating the pods in my network and start up my application. Okay, so far so good. Looking at this JSON files, it's a little bit important to actually understand this for the later steps. There's a few important parts in such a JSON file that specifies a controller. First of all, you see on the top that there's a number of replicas. And that's the number of pods that we want to have in the running cluster. Then there's all kind of labels that we have. We will not go into that very deeply, but labels are used all over the place in Kubernetes to link the different concepts like replication controllers and pods together so that they know about each other and know that they belong to each other. And then at the bottom we have a specification of a container, and that's basically a specification where I say, well, I have here my container that contains my component or my application, and it exposes, in this case, port 80. It doesn't necessarily mean that port 80 is directly exposed on the host machine that this will be running on, but I just say, well, the container will expose this specific port, and later on we will see how to use that. All right, so we have our first deployment running using this kubectl tool, and now we want to start doing some scaling. So again, we can use this kubectl tool and say kubectl scale, give it a new number of replicas, and the replication controller will take care of starting new machines or starting new pods on my machines, or stop some running containers. Again, so far so good. Here it starts to be a bit messy. So in this case, I want to update a running application. I have my application running on my cluster, and I have a new version of my container, and I want to update it. So what do? Well, I have to create a new replication controller, which defines that I want to have some number of replicas for this new version of my container. Again, I have to use this kubectl create command, and then I have to, well, decide at some point to downscale the old cluster. Well, you kind of start to see here, this is all not very automated, and there's a lot of manual typing in kubectl, and well, especially the downscaling part is a bit messy here. When do I downscale, and how do I synchronize this update with my running zero downtime policy, for example? So this is probably not enough. We need a lot more. So let's start simple. Let's start to automate this deployment process. Let's see if we can get some automation going on that we can actually do an initial deployment and an update of my application without actually using this kubectl tool. That would already be a step forward. Mind you, this will be the simplistic version. This is not how we will end up. This is just the first step towards full automation. So the first thing that you should really realize when looking at Kubernetes is that Kubernetes is not just a tool that you use and everything will just happen magically and, well, your containers will be running happily ever after. Kubernetes is actually more of an API. It takes care of a lot of lower level networking stuff especially. It's very good at that. But, well, it's not an end-user application that just takes care of everything for you. But it does have a API, and that's what we will be using to build on top of and fix those issues or missing parts of what Kubernetes doesn't have yet out of the box. So let's say that we want to have a build server, and this build server is going to run a build, and that build should result in a deployed application. So basically that will mean that my build server is just going to use REST to talk to the Kubernetes master, to its API, and instead of using this kubectl tool to create a replication controller, we're going to use an API to create this replication controller for us. And at the end of the deployment, the build server will also use the same REST API to actually scale down the old cluster and finally delete it. So the picture starts looking like this. We have our build server. The build server also takes care of pushing our registry or pushing our containers to the registry, and then just invokes the API over HTTP, and well, the rest of the story looks similar as before. And the command looks a bit long, but actually this is just a very simple curl where we invoke the API. We see it's just all HTTP. And in the JSON that I left out here, you just have the replication controller definition as I've shown previously. This works, kind of. Because if you start thinking about it, does this actually give us zero downtime deployments? Well, it might or it might not. It depends. So what I've shown just now is that at the end of this build step, the build server must take care of downscaling and deleting the old cluster. Well, if there is some waiting period and making sure that the new version of my application is fully running before I start downscaling the old one, well, then probably I will, in fact, have a zero downtime deployment. But what if the build server doesn't wait long enough? Or what if my new application doesn't come up at all because I deployed a version that actually doesn't work? Well, then probably my whole system will just go down and people will start screaming at me. So that means we are just not quite there yet. We did some automation, but this is not something that you would use in production. It's just not complete yet. But before going into that, we have some bigger fish to fry, because how do we actually get to our running application? So we have a running deployment now, sort of. But how do we actually access them? Let's say that we have a web application deployed, and we want to use a browser to actually get to that web application. Well, what do you access it on? Which IP address do I go to actually get to my web application? Well, if you look at Kubernetes, you see that a pod, an instance of my running application, as we've seen before, they can come and go all the time. Kubernetes can start new pods when I scale up. It can decide to reschedule if a machine is busy, for example. So that means pods can move around my cluster. And as a user or developer, I shouldn't care about that. Kubernetes should be knowing what it's doing. But it does mean that my pods will not stay in the same place. It also means that my pods have dynamic IP addresses. And I don't even know what that IP addresses will be. So, well, first of all, I can't actually access those pods directly, because I don't even know where they are or who they are. Then there is a second concept in Kubernetes. And that concept seems to fit very well with the thing that we want to be doing here. But as it turns out, it's maybe not a perfect solution. So the other concept that we have are Kubernetes services. And a service is basically a proxy that you can put in front of a number of pods. So the pods are all dynamic. They have dynamic IP addresses. You can put a service in front of it. A service has a fixed IP address, or at least we know the IP address, and it will not change all the time. And if we tunnel the traffic just to the service will take care of then balancing it through to my pods. Looks like some form of load balancing. So this is how we started out. Services seem to fit our needs perfectly, so we put just a service in front of all the applications that we deploy. That's a proxy, simple load balancing, and it all looked good, until we looked at it a little bit closer. Because if you actually take this to production, well, there's some other questions that you have to answer. For example, how do you do SSL offloading? Well, Kubernetes services don't do SSL offloading because they are in fact not HTTP load balancers. They're just proxies to my pods. They're much simpler. So, well, does that mean I have to actually take my SSL connections all the way to the pods? That's not convenient, probably. What about some proper form of load balancing? Because the Kubernetes services literally do round-robin load balancing, which is not real load balancing at all. What about things you normally expect in a HTTP load balancer, like redirects and rewrites and all that kind of stuff? If you've ever looked at Nginx or HA proxy, you know there's loads of configuration that you can set there. Well, there's not really a place for that here. And then we have another problem, because that fixed IP address that we had with the service turns out to be actually not that accessible from the outside world. That IP address exists within the Kubernetes cluster. I can use it to communicate from one container to another container, but it doesn't mean the outside world can actually see that IP address. So, well, we didn't really get anywhere with services here. We will see services again later on because it is actually something very useful, but probably not the right concept right now. Because services are designed in Kubernetes to facilitate inter-pod communication. So I have different containers. Those containers might run microservices in that kind of architecture. They might need to communicate, and services are the way to facilitate that. But they are not meant to be used as HTTP load balancing, although the concepts look similar. So we take it a step further, and we introduce our own load balancer. What we do is we take our load balancer. In this case, it's a Vulkan proxy, but that could be Nginx or HA proxy or some other load balancer that you have. We just put that on a fixed IP address, probably just the IP address of some machine that I dedicate to this in my cluster. And the proxy in this case is going to do proper HTTP load balancing, including SSL offloading, etc., and then pass through the traffic to the pods. It does mean that my proxy needs to know about my pods. It needs to know those IP addresses, and it needs to be able to access those IP addresses. Well, in this case, you see also something new in the picture, which is etcd. If you look at load balancers out there, well, you probably know about things like Nginx and HA proxy, but Vulkan is a quite new load balancer, which is nice. Because all the configuration for Vulkan is stored in etcd. And etcd is a key value store which is highly available. And the nice thing is that Kubernetes also depends on etcd. So if you have Kubernetes running, you also have etcd running, and it means that the infrastructure is there anyway. So why is this nice? Well, we're in a very dynamic environment. Pods are coming and going all the time. And that means my load balancer has to be reconfigured all the time using APIs. And just using a key value store for that is actually very convenient. If you would be using Nginx or HA proxy, you can do the same thing basically, but then you would need to do some templating. So you basically have a template of a configuration file, use that template to generate new configuration files, and then you have to reinitialize the load balancer with that configuration. Well, this looked nice on paper, but actually it turned out not to work either. Because, well, my pods are not visible from the load balancer. If I put Vulkan or another load balancer on a separate machine in my cluster, like I did on in the picture just now, again, that machine doesn't know about the virtual IP addresses that Kubernetes uses internally. So it can't actually access my pods at all, which is probably problematic. Which brings us to the next step. We're going to introduce another concept, which is virtual networking. And you can use Weave for that. There's some other tools like Flannel, which work just as well, but we're using Weave currently. And with Weave, you put a virtual network, basically, that you define, which Kubernetes uses, but which can also be used outside of Kubernetes. In that way, well, each pod still gets its own IP, so we don't have problems with reusing ports, for example, on an IP address, because each container gets its own IP address anyway. But we can now access the pods from outside of Kubernetes, and that's exactly what we needed. So we still have the same setup. We have a separate machine with a proxy, and we have the machines where the pods are running. And we put a virtual network on top of it, in this case facilitated by Weave. And Weave takes care of actually handing out IP addresses. That's quite convenient. As I said, there are different solutions out there as well. Doesn't really matter which one you use. All right, so we have quite a few things working already. We have some kind of automated deployment. we have basically load balancing solved as well. But looking at the load balancing again, well, you might have another question: how do we actually keep track of pods? Because, well, I might scale up, for example. So I have my replication controller defined, but I scale up to use more machines. How does my load balancer actually know about those new machines? How does the load balancer start using those new machines? Well, for that we introduce another tool outside of Kubernetes. And let's call it here in concept a registrator. And I have a more concrete tool in a minute. What we do, we have a process running, and that process is watching the Kubernetes API. It's actually a feature of the Kubernetes API. We can put a watch on the API, and we can, for example, say, I want to be updated of all changes to pods. So every time a pod disappears or a new pod is started, I will be getting a callback, and I can execute some code. The registrator on its turn will take this new pod, if a new pod registration happened, register that pod in etcd, my key value store, and Vulkan, which uses etcd to read its configuration, will use this new data to actually reconfigure itself and start using those pods. Actually, quite simple. And again, you can do the same thing using something like Nginx. We probably can still register our pods to etcd, and then Nginx can use a template file to regenerate the configuration file based on this new set of pods and start using them that way. So a little while ago, we created this thing for ourselves, and we tested it for a while, and then decided that this might be useful for others as well. So we open sourced it, and that's called Amdato Vulkanized D, because, well, ending things on D seems to be the thing in this world. So that's what we did as well. It's written in Go, because that seems the other thing to do in everything related to Docker and Kubernetes, etc. And that actually has a nice side effect, because that means the binary that we produce is extremely small. And that means that it's very easy and with very little overhead to actually start running that tool. It's also available as a Docker container, so you can just do a Docker run and pass in the etcd URL and the Kubernetes URL, and this will basically take care of the rest. So that might be useful to take a look at. So that means where we just had the registrator as just a concept, we can use the Amdato Vulkanized D tool to actually make this all work. It's not a very advanced tool. It's about maybe 150 lines of Golang code, so it's not very large, but it does do what it needs to do. All right, so we've got a load balancing problem more or less solved. But we still don't have a proper way to actually update the application. We have seen that we had some kind of automation there, but we didn't have any guarantees that, we don't have any downtime while doing such a deployment. So let's see if we can actually get something like a Bluegreen deployment up and running. So a Bluegreen deployment is a deployment where you have an existing version of your application running on a cluster. Let's say we have 10 machines running the old version of the application. And the way to update this deployment is start my new version on another 10 machines. Make sure that everything starts up completely. Maybe do some health checks, etc. Make sure that everything looks good. And then we just switch the load balancer from the old version to the new version in a single go. If everything still looks healthy, we can then scale down the old cluster and just continue using the new one. The nice thing about such a deployment is that it's quite safe. You never have the scenario where there's two versions of your application or your components running at the same time. Because if you are doing that, you might have all kind of problems with scheme updates, one using the old scheme of your database and the other one using the new scheme. So it can get quite complex. Doesn't mean you always want to do this, because you do need to have the capacity on your network to actually run 2 versions at the same time. But given you have that, blue-green deployments are quite nice to have. So we need some kind of mechanism that does the following. First of all, we want to deploy the new version of our application and scale up a new cluster for that. Then we need to wait until it's healthy. And waiting until it's healthy also means that we have to have some kind of way to know if it's healthy or not. So we need some kind of health check mechanism. When everything looks healthy, we just switch the backend in the load balancer. So all the traffic that comes into the application now uses the new version of the application. And then we can just dispose the old cluster, and the update is complete. If something goes wrong halfway, so for example, we do scale up the new cluster, but our health checks fail for whatever reason, maybe configuration problem, maybe the version that I deployed is actually broken and will never start at all, then we probably just want to kill the deployment. The old version is still running, so there's no immediate problem. We can just take our time to fix a problem and try a new deployment. So that's why it's nice to have this blue-green mechanism. So the first question that we have to answer to make this to work is, how do we actually know if and when a pod is healthy? Well, the first answer could be you just look at the status in Kubernetes. In Kubernetes you can look at a list of the pods that you have, and it will tell you the status of such a pod. Well, if everything looks good, the status will be running. But that doesn't mean everything is in fact running, because it just means the container is started. It doesn't mean that the process that runs in the container does anything useful. So for example, if you have a Java application that runs in a container, well, the Java process might need some time to actually start up, do stuff, read configuration, and actually become healthy. But way before that, Kubernetes will already tell you it's running. So we need to look a little bit deeper. Because in the end, we need this. Our deployment server or deployment process needs to be looking at our pods, and the pods need to tell if they're healthy or not. So what we did in our applications is actually provide a health check. And this can just be provided on a HTTP URL. So for example, we get /health. And if /health returns true, then we're happy. If it gives a HTTP status code which doesn't look good, or doesn't return anything, or it returns false, something is not healthy with this pod yet, and we either have to wait longer or decide to terminate the whole deployment. Once we have that configured, we can start using it from the deployment process. But remember that we were running this whole thing from our build server. And if you see all the different steps that we have to take now to actually do a deployment, you also start to see that this all starts to be quite complex. First, you have to create a replication controller. Next, you have to have the waiting process to look if the pods become healthy. There might be some kind of rollback mechanism there as well, in case they are not getting healthy. Then we have to scale down the old cluster. So it's quite a lot of steps, and you probably don't want to script that over and over again on your build server. And then we have another problem, because our build servers are probably not running in the same virtual network as our container infrastructure. At least in our case, that was it was like that. So that also means that the build servers that we have can't actually access the pods directly to do the health checking. Very practical problem. Of course, you can fix that by running Weave on the build server as well, but in our case, that was not really an option. So we decided to actually create another process that we run in the network, which we just call the deployer here. And this deployer listens on or exposes an HTTP interface again. So our build server can just do a curl or something like that to start a deployment. But the deployer process will take care of all the different steps that we need to get a full blue-green deployment. So it will talk to the Kubernetes API to create a replication controller. Kubernetes will actually start the different pods on the different machines that we have. The deployer, again, will start looking for the pods that we have. So we know that we, for example, need 10 pods to run. It will wait until 10 pods, at least, are healthy. If that doesn't happen within a fixed time, we can roll back the deployment. And the deployer also talks to etcd so that at some point we can switch the load balancing configuration. So adding those parts back to the picture as well. We still have fuckin, of course. Fuckin is still looking at etcd for our backend configuration, and the deployer makes sure that this configuration is written to etcd. And we still have Amdato Fuckin ISD that takes care of actually tracking the pods and making them available to the load balancer. So you see there's quite a few components involved there, but in concept it's not that difficult. And again, this deployer, the implementation that we have, which is not open source yet, might or might not be open source at some point. But it's some code, but it's not a lot of code. I mean, you can actually do this. So the other thing that we get from this deployer that we have is that we have a deployment descriptor now. So the way we implemented the deployer is that we have a JSON-based deployment descriptor, and that's what the build server uses to post or to request a new deployment. So we can either enable or disable the health checks. Let's say that we want to deploy some application that actually doesn't have health checks and we can't change that. Well, you probably want to turn them up, otherwise nothing is ever going to be deployed. We have to specify the version of the application, and we're running on Bamboo as a build server. Bamboo can give you the version of the deployment that you're doing. You can pass in yourself there as well, of course. An application named Replicas, which makes sense. And because we're working with the load balancer directly, we also have to specify which front end in the load balancer to change. Because otherwise, you could only have one application running in the cluster, and that doesn't make any sense. Next, we have the pod specification section, and that's just the pod specification as we've already seen it. So this is just the API, which is part of Kubernetes. In this case, again, a container and the fact that it runs on port 8080. We also see the interaction of environment variables here. And for example, here I push the version of the application, or actually the version of the deployment. I push that to the application so that we can start using that in our container. And a little bit more about that kind of configuration later on. Well, we started using this for a while, and everything looked pretty good until we started noticing that once in a while, it seems pretty random, replicas were started on the same physical machines. So I deployed an application, I specified, let's say in this case I have two physical machines, I specified I want to have two replicas, and I would see that the first application that I deployed would both be started on the first physical machine. The second application that I deployed would both be running on the second machine. And then you're kind of missing the whole point of replication, because the whole point of replication is that, you have some form of load balancing, and you have a form of failover. If one of the physical machines fail for some reason, I don't want my application to die. But if both of my replicas are started on the same physical machine, well, what happens if the machine dies? Of course, everything is broken. So I started digging in Kubernetes, and I started wondering why this happened, because it looked very strange, but it turns out this is actually by design. And the way to force Kubernetes to actually do the proper scheduling and make sure that they are not started on the same physical machines is to introduce a service for a component that you deploy. So I'm deploying my application. I want to make sure they are spread across the different physical machines that I have. That means I have to introduce a service on top of those pods. Basically, it means I need a service for every deployment that I do. If the service is there, the service doesn't have to do anything, but it must be there. If it's there, the scheduling will work correctly. That means we just introduce a headless service, as they call it in Kubernetes. A service that doesn't actually expose any ports. It's just there to take care of the scheduling. So that's another step that the deployer has to deal with. So just a little example of how this could look like. So I have an application running. We see it's on release 83. This release version is passed in as a variable. And let's see if we can start a deployment. Oh, there we go. So we have Bamboo here. Bamboo builds a Docker image. In this case, the Docker file is included in the build. You could also just provide it as a file, of course. The next step is that we do a Docker push to the registry that we have. And then the important part is the script that we have, where we do a curl to our deployer. You see it's just HTTP. We have the deployment descriptor, as I've just shown as well. A bunch of environment variables. And from there, we can just click deploy. Click. And in Bamboo, you can create a deployment of a specific version that you have built. You just click build, and from here I speed up the logs a little bit because otherwise it takes a while. But we see the Docker push happening here. And now on the in the Kubernetes cluster, this is the logging of the deployer that we have. So this is just the deployer process that we have. We see that the deployment is running. We can start looking at the pods that we have in Kubernetes. And we see that both version 83 and 84 are now running besides each other. But the new version, version 84, is not being used at all yet. The load balancer doesn't yet know about it. Here you see the health checks happening. So we're just pulling the pods and see if they become healthy. And once they become healthy, we switch the fuckin backend and we delete the old cluster. And we see we are now on release 84. Well, this small demo didn't really prove that. But if you actually fire a load balancer or load testing tool like Gatling, for example, you can actually fire HTTP requests on this application. And even during the switch, you will see none of the requests will fail. So they will go to version 83, well, until we do the hard switch in the load balancer. And from that point on, everyone will go to version 84. And there's no loss of traffic and no downtime at all. Which is quite nice to do, and especially important, of course, if you're doing a lot of deployments to production, which more and more people start to do more and more often. And with this mechanism, it's quite safe to do so. So based on this mechanism, we can do another thing, and that's testing in production, because what else would you need? Of course, testing in production is a crappy idea, but in some cases, it might actually be useful if you want to do feature testing. So we have, of course, all our tests during development up and running, but we want to test if a certain implementation of a feature works better than another implementation of a feature, or if the feature works at all, if customers like it. So a lot of especially larger companies do this quite a lot. They basically test features in production and see how people respond to it. And given the deployer mechanism that we've just seen, this is actually quite easy to implement, at least from a infrastructure perspective. Because this is just a different strategy for the deployer process. We still add the replication controller, so we scale up some new machines running some alternate version of our application. But we don't actually scale down the running cluster and completely switch to this new alternate version, but we keep it running. So that means that for Fuckin, our load balancer, there's two versions running in parallel, and it knows about both of them. Most of the traffic will be redirected to the main version of my application, just the version that we know is stable and the version that works well. And some of the traffic, if you're that unlucky customer, will be directed to the Canary version of our application. And that way we can test out if this feature works, maybe test out some performance implications, etc., etc. If we're happy with it, we can just scale up to more canaries, maybe do a 50-50, and if we're very happy with it, maybe we turn off the first version and completely switch to the newer canary version. So that's something we basically get for free, given this whole mechanism. Another question that you see a lot when people talk about Kubernetes is, how do I actually work with persistent data? How do I deploy something like Mongo in Kubernetes? Well, you don't. You can, and there's quite a lot of examples that show you how to do it, but it just doesn't make any sense if you ask me. Because if you look at Kubernetes, Kubernetes is really great for running stateless containers. Why stateless containers? Well, the thing that we want to achieve is we want to run a lot of containers together. We don't want to have one container running on one machine, and that machine just running that single container. No, we want to have multiple containers running on a physical machine, but every container is probably also replicated on many machines. And the implications of that is that the containers are moving around. We've already seen that. When you scale up, they appear on some machine. We never know which machine. Kubernetes might decide to just reschedule and take a machine or take a running pod and move it to a different machine. Well, if you look at what we need for data stores, that doesn't really fit so well. Because reactive scaling for data stores just doesn't make a lot of sense. This strongly depends on which kind of data store you're using, but let's take the example of Mongo, for example. Well, starting a new replica member in a replica set, that's the terminology in Mongo for nodes in a cluster, it's quite expensive because all kind of synchronization have to happen in a cluster, and you will lose some performance while the synchronization happens. So adding new machines and removing them a minute later in a stateless web application might make sense if you have a burst of load, but it doesn't make any sense in Mongo because you will probably do more harm than actually help anything. Also, you see that data stores are still quite often a bit of a bottleneck when it comes to performance. Scaling data stores is just not easy. And that means that the hardware that this cluster is running on should probably be tuned. If you look again at Mongo, you want to make sure that the size of the memory fits the size of the data set that you're working with. You want to do some I/O optimization. So if you're running in a cloud, you want to have better guarantees of the IOPS that you want to pay for and want to use. And in general, scaling is just expensive. So you don't want to, well, you want to make a choice to add new machines to your cluster, scale those machines instead of that happening all automatically. So that means this just doesn't really fit with the whole dynamic nature of Kubernetes. That's a nice side effect because now, we just look at data stores as a different concept, which is also deployed in a different way. So we have our infrastructure servers that run our load balancer and the deployer tool, etc. We have the Kubernetes nodes that actually run our software, and then we just have a separate cluster or clusters running things like Mongo, Elasticsearch, etc. That also means that we don't have to, ask ourselves anymore, how do you deploy something like Mongo in Kubernetes? Because it seems to be quite difficult to do that. Well, we just don't do that at all. I don't want to say that this will never change, because there is progress as well in working in a better way with persistent data in Docker in general, including Kubernetes. So maybe this story will be different later on, but for now, this is probably the best way to deal with it. Another topic, how do we deal with logging? Because, you see that we have a whole bunch of machines, and those machines are running my pods. That means that every component in my application might be running on many machines. That also means that I never really know where my application is running exactly. So if there's a problem, if a user reports a problem, and maybe give me some key in the logs, where do you start looking? Do you SSH to one of the many Kubernetes nodes and look at one of the many replicas of your application? Well, chances are that you will never find the logs that a user reported to you, because those logs are on a completely different machine running a completely different pod. So kubectl logs, which basically just gives me the system out of a container, just like Docker logs, that's just not enough. It's not good enough. Something that you have to get into very early when starting to do this kind of deployments is centralized logging. It's probably the first step to get into once you get the basic infrastructure running. And the assumption should always be that you just can't access a pod, which might actually be the case because if you're running a Kubernetes cluster, you might not want to have all the developers in your organization that deploy to this cluster also have physical SSH access to those machines, because, well, they might do a little bit more than just looking at the logs, which you might want them to protect for. So one of the very useful tools in this area is the ELK stack, Elasticsearch, Logstash, and Kibana. There's other tools as well. There's plenty of good tools, but ELK is what we currently use. And that means that your Docker containers must be configured to start logging to Logstash. And Logstash just accepts all the logs, maybe do some formatting on it, forwards it to Elasticsearch, which is just a data store in this stack. And we use Kibana to generate dashboards on top of that to actually look at the logs. So once we have this in place, what we have is all the different components in our infrastructure, all the different Docker containers, but maybe also the infrastructure that we run, all end up in the same log store. And that means when we start looking in the logs and start searching in the logs, we have the logs of all the different machines and all the different pods instead of having it from a single pod. That also means we can actually track through our whole infrastructure where a request went. And well, there's a little bit more to it than just having this infrastructure in place, but the infrastructure is definitely step one. There are different ways to actually get this to work. So the simplest way is to forward simply again the system out of a Docker container to Logstash directly. There's tools available for that. And that way, well, if you just log to the system out, they will end up in Logstash. And that's a good approach if you don't have more control over the logs. If you go a step further, you can actually, that's what we did with our applications, we actually have components in our applications that know about Logstash. And that way we can have a better, formatted logs. We can actually log deeply nested JSON structures if you would want to, instead of just having, single lines of logs that are a lot harder to parse. But that's just a choice that you can make. You can use both, of course. So in our case, it looks like this. Let's say we have an OSI application. The OSI application, which is basically just Java, of course, either uses SLF4j or the OSI log service. Logs from there are forwarded to Kafka. So we have another indirection there to make sure that we can handle very large volumes of logs without overloading the Logstash servers. The Kafka queue is consumed by Logstash, and maybe some other infrastructure components which don't work with Kafka log directly to Logstash. Logstash forwards everything to Elasticsearch, and our developers are looking at the Kibana dashboards on top of that, looking at pretty graphs, etc. So this would basically just be looking at the logs itself, and there you can look at exceptions, search, and etc. So that's quite nice. So then finally, step 9 is working with configuration, because you will notice that, of course you start working with containers, and probably you don't just have only your production environment. Probably you're running different environments on top of Kubernetes. You have your production environment, test environment, acceptance environment, and whatever environment. And somehow you need to configure your containers to use the correct data store, use the correct credentials, etc., etc. Well, you could hard code them in your containers, of course. That's one approach, but that means you have to rebuild every time you want to move to a different to a different environment. But you can also have some kind of dynamic configuration. So one approach that we use a lot is use environment variables. So if you look at our configuration files, in this case just a simple property file, we have variables in that. So this Mongo host is actually a variable, and this variable is picked up from the environment variables. Well, depending on the frameworks, languages, and tools that you use, there might be different ways to actually read those from the environment variables, but whatever you use, there's always a way. And that means in our deployment descriptor that we have on our build server, which is passed on to the deployer tool, we can just have environment variables specified. This is just part of Kubernetes. And there we have key values, and that actually contains the specific value for, in this case, this Mongo variable. So just using the fact that we can somehow read environment variables from our container to our application, this all works. So the fact that this is introduced as an environment variable is taken care of by Kubernetes and Docker. The rest is up to you. So that's one way. The downside of this is that it's not truly dynamic. So this works as like a one-time shot. You can have different builds that produce or deploy to different environments. That's pretty good. But what if you actually want to change this Mongo address during runtime? Well, I'm not going into it if this would be a good idea or not. That completely depends on the situation. But a nice way to actually get that to work is, again, use our key value store that we have anyway, etcd in this case, because Kubernetes uses etcd. And all the configuration of our application is actually not stored in property files at all anymore. So the only property that we actually deploy in our application is the address to etcd. And with etcd, you can even use a proxy on every machine, and then you can just use localhost 2375, and it will magically know how to find the actual etcd nodes. In etcd, we just have a key for our application, and in that key, the value is just a piece of JSON containing all this environment variable listings. Now, of course, you have kind of a new problem, because your application has to know how to actually read this from etcd and do something useful with it. Well, for etcd, that's quite easy. There's client libraries for a lot of languages, and even easier, you can just use HTTP to do a HTTP GET on this key. You can just parse the JSON in any language and do something with it. For dynamic configuration, it might be a little bit harder. If you look at OSGI, dynamic configuration is like, well, is there by default. If you look at something like Java EE, well, actually, that's not how it works out of the box. So you might need other tools and libraries to make it truly dynamic. But at least from the infrastructure perspective, you can get it to work. So different ways, you can mix and match them wherever you want. But this seems to work quite nicely. All right. You might get the impression of all of this that this is complex, difficult, and a lot of work. It is. Because there's just a lot of parts to get right. The project I'm working on is actually offering that as a service. So if you really don't want to do this, actually, I do recommend doing it because it's a lot of fun. But if you don't want to or don't have the time, you can just pay us to do that. And with that, some references to my blog. I recently started writing quite a lot about Kubernetes and related topics. And with that, I think we are at the end of the talk. So everyone, thanks for being here.